So how do we, well, it is our tremendous pleasure to hear from Donal to close out what has been a spectacular QCD Meets Gravity.
Okay, yeah, well, let's get started. I just want to start, of course, by thanking the organizers, giving me the opportunity to speak and for going to all the effort of organizing the conference. It's fantastic. It's been a lot. Yeah, you know, this is our last talk at the meeting. And, well, you know, the idea of QCD Meets Gravity is that maybe it's a good idea for QCD people, you know, Amplitudes people, to talk to gravity people. You know, maybe with some foodstuffs around, you know, different foodstuffs in different places, I guess. Now, I think we've seen, you know, it's a really good idea. We should keep talking. There's a lot of good ideas. I think people would agree that we're all learning a lot from whatever, you're a more Amplitudesy or QFT person or a more gravity person. And there really has been a lot of remarkable new ideas and results presented during the meeting, so it's very exciting. But, you know, this is the last talk, right? You know, it's late. You know, maybe it's not late in LA, but it's late in the year. It's not late in the day. It's pretty late here in Edinburgh. So this is going to be a bit of a different talk. I'm just going to relax a little bit, you know. Rather than going into details of results or, you know, sort of trying to explain something, I'm just going to dream. Right? You know, imagine, you know, what could happen if we did things a little bit differently. So rather than having QCD meets out gravity, suppose we have QCD defines gravity. You know, by which I mean, suppose we just try and get everything from the start, from the scattering amplitudes. No Lagrangian, no action, no path integral, right? But we still have the amplitudes. So how do we then think about things? Well, you know, we've got a good place to start, right? I mean, there's a lot of fantastic information you get very quickly from scattering amplitude. So, you know, we know that there's a unique 3-point amplitude for gravitons. We know that once we've got that 3-point amplitude, we can use BCFW to build up higher trees. We can use the unitarity method to paste all of these trees together to get any loop diagram we want. So in that sense, we know that once you start from scattering amplitudes, you're going to have all of the nonlinearity, you know, you get the full nonlinear structure of the Einstein-Hilbert Lagrangian. It's one way of thinking about that. But there's much more to gravity than, you know, nonlinearity. It's not like if you pick up a GR textbook and you leaf through its pages that they spend a lot of time, well, not all of them at least, going on about the nonlinearity of the Lagrangian. Instead, the textbooks tend to think about things like, you know, the Schwarzschild solution, that's pretty cool. There's these geodesics, you know, those are pretty fantastic. There's gravitational waves, which is, you know, obviously very exciting at the moment. So can we get all of these things from scattering amplitudes? And well, you know, I want to get it directly from the amplitudes without recourse to other information. And one thing I think, you know, you should always bear in mind is, you know, it should work, right? I mean, I think it was DeWitt who first said this, you know, that the only observable in quantum gravity in asymptotically flat space is the S matrix. So, and if you believe, as I do, that the classical theory arises as an approximation to the quantum theory, it should be that all observables in the classical theory, you know, in particular, can be obtained from the S matrix in asymptotically flat space. So you should be able to get every observable thing from the amplitudes. Okay, now what I want to do is then just start with, you know, just like an amplitudes first. We start with the amplitudes, we look at the loops and legs. So I'm going to start with the simplest amplitudes, the 3-point amplitude. Now, a good one to look at, a simple amplitude, is an amplitude with a massive particle coupling to a graviton. So again, it's unique up to some overall scaling, this kappa here. You know, the m is just some polarization vector. It's not with one of the momenta. It doesn't matter which one. There's some number running around. This is a spin 0 amplitude. So it's just an amplitude describing a point mass coupled to gravity. And the point I want to emphasize about that is it's unique. And that makes sense because there is another unique object in gravity associated with point masses, right? It's the Schwarzschild solution. So this thing, this 3-point amplitude, silly as it is, should just be somehow the Schwarzschild solution. No? All the information should be there. Okay, well, with that in mind, how can I extract something, maybe familiar to a relativist from this 3-point amplitude? One thing you'd want to do is, get some space-time, right? I mean, the amplitudes are in Minkowski space. Somehow from the point of view of the amplitudes are in momentum space. Amplitudes, as we often work with them, are very simple in momentum space. Of course, you can write them in position space, but from this perspective, I'm taking the momentum space amplitudes as the basic things. The momentum space is the thing that you start with. The position space stuff comes about, I guess, by a Fourier transform, right? I'm just going to Fourier transform this amplitude. Well, one other thing about that amplitude is it has 4 spinners in it, right? There are spinners of some specific type. So, say square bracket spinners. So they have some helicity scaling. So to get something sort of invariant in space-time, what I want to do is get rid of that scaling somehow. So one way I can do it is multiply across by 4 spinners of the other chirality. Right? So you can consider an integral like this. So it's a Fourier transform integral. And there's a space-time here, e to the I k dot x. X is appearing, position is appearing through the Fourier transform. Here are my 4 spinners and the scattering amplitude. So it's a natural thing to think about. I mean, it's the most dumb thing you can do, right? Now, one comment, of course, as David was emphasizing, the integral we have to do is an on-shell integral. It has to be on-shell because the amplitude is on-shell. I can't take this off-shell. I really have my amplitude hat on here. So that means we have to do some analytic continuation. Right? So fair enough. I'm going to do that. I'm not going to apologize. I don't think we should. So I'll analytically continue either to complex momenta, as we frequently do, or to this split signature space. I do the calculation that analytically can continue to Minkowski at the end of the day if you want. Now, there's the interesting thing that you find when you do that integral, which is that you get this spinorial curvature. Now, the thing to emphasize here is it's exact. That's the exact spinorial curvature of the Schwarzschild metric. So you get it from the usual curvature by introducing some spinner somehow and hitting the space-time indices with signal matrices. So that's the ball spinner. And it drops out immediately when the scattering amplitudes, and it turns out that the result is exact. Okay, well, that's a good start, right? But actually, there's more to say at 3 points, quite a bit more. So one thing we can do is, take these 3-point amplitudes. So I want to emphasize here, of course, there's really 2. I'm talking about the 3-point of massive particles. But there is, of course, the 3-point amplitude somehow in the field. It's not so important in this story. Maybe we can discuss it later if people want to. But one thing I can do, you see, is I know that this amplitude is defined up to overall scaling. Now, here I chose that both numbers were real. Some say there's some factors 2 or something between these. That doesn't matter, but they're both real. Now, they don't have to both be real. What has to be the case is that, the opposite helicity has to be the complex conjugate of this one here. So if I have M3 plus with some number, then the number in front of M3 minus has to be the complex conjugate. So what I can do is I can misalign these amplitudes. I can put a complex number here, keeping that as a real number. That kappa there is real. This one is now complex. So this is some misalignment. And because I've dialed the massive amplitude but kept the other one, it's a physical transformation. So this changes things. And when you do that, you just compute this Ball spinner thing again. You ask yourself, what do you get? It's picked up this e to the I theta factor. What's that? Then it turns out it gets another exact thing in gravity known to relativists. It turns out that's the Ball spinner of this Cavenut metric, Cavenut spacetime, has 2 parameters, a mass and a nut charge. They're related through this angle. Okay, so we get that too. We can go further. So another deformation of the 3-point amplitudes, which has received a lot of attention, obviously very important, is to switch on a spin, right? And we do that by introducing a spin parameter, A, the spin of the body. I've chosen the specific one, the minimally coupled one. And when I switch that on, go through the same calculation, well, the A here talks to this X here and just generates a shift. And again, that's a known thing. So with the theta and the A, this is a Wahl spinner. Again, it's exact. It's the exact Wahl spinner of a Kerr-Taub nut spacetime. So if I switch off the theta, I just have Kerr, exact Kerr. If I have them both, I have this more exotic object, Kerr-Taub nut. And it all just falls out through an on-shell Fourier transform of the 3-point amplitude. That's all it is. So it's great, it's actually very easy, right? But there is more to say about this. So, well, one thing, just to hammer home this point, as a scattering amplitude person, I think it's good to be on shell. Very good. It's a good idea. So we do care about that. We know that 3-point amplitudes don't really go on shell in Minkowski space. So, this continuation to split signature, I think it's important. It's something that maybe in a bit weird if you're not an amplitudes person. But I think if you want to think about general relativity, if you want to take the lessons from scattering amplitudes really in the classical theory, you probably want to take this continuation seriously. I'm happy to see. I'm not the only person saying this. Alfredo and his friends at Harvard recently wrote some beautiful papers on this, contributing quite a lot more. Anyway, so that was also a topic that David just discussed a few minutes ago. Okay, now, next thing. I recovered, I was emphasizing, I recovered the exact Wahl spinner. But you really have to wonder what that means. It's true, but there's asterisks, right? And the asterisk is what is meant by exact. So in general relativity, in the classical theory, I can take these spinners and perform a local Lorentz transformation. So that means that I just choose a different basis of spinners, basically, at every different point in spacetime. And I can put, I can make that as complicated as I want, and I can take that Wahl spinner, which we got from the scattering amplitudes, and I can make it look as complicated as you want. So it doesn't always have to look as simple as it does coming from the scattering amplitudes. Now, the classical physics here, it's a little bit complicated. So these spacetimes, these Schwarzschild Kerr and these funny nut spacetimes have the property that they're Kerr-Schild or double Kerr-Schild. So they have this Kerr-Schild structure, maybe a little bit more complicated in the simplest case. And it turns out that the curvature linearizes, the Riemann curvature linearizes in these appropriate coordinates. So one way you can think about this is, somehow in doing this computation of the scattering amplitudes, I just set all as Fourier transform, the X is coming in that way, right? But, something's happening there. Is it that the quantum field theory is picking intelligent coordinates somehow? I mean, maybe you should just say this, this calculation happens to be, it's really just a linearized calculation, and it's just a coincidence that the linearized theory happens to give the same answer as the exact theory. So the point of view, I don't really know what's going on here, right? But you might think, if you're optimistic, if you really want to think that, QCD defines gravity, you might think that the quantum field theory is making something obvious that the classical theory isn't. The classical theory is making us obscure. Okay, so that's all I wanted to say at 3 points. Well, except maybe, yeah, I guess Ira was asking about gauge stuff. And I think, if there's gauge stuff sneaking in, it's here, right? It's in the choice of X there. It's in coordinates there. Okay, well, in scattering amplitudes, if you finish talking about 3 points, probably time to start talking about 4 points. 4 points is something that we're really very good at. QCD meets gravity. 4 points, you know, do potentials, we can do impulses, we could do effective actions, we could take spin into account. This has been the topic of very many talks at this meeting, just not this one. I'm not going to really talk much about 4 points. You know, it's very good. We're good at it. And I guess the point to make is that, you know, in terms of the classical physics, you know, this is, you know, those parts of the textbooks about geodesics and geodesic deviation. This is all this stuff. I take one of the particles very heavy, the other one, you know, looping around it. Yeah, we can do that. Okay, well, after 4 points, we go to 5 points. 5 points was the subject of David's talk. Waveforms. Waveforms, obviously very important, gravitational radiation. This is occurring at 5 points. And we encounter, and it's an interesting topic, you know, essentially, if you wrote this thing down, you say, well, look, I've got a 5-point amplitude on Fourier transform it. Well, that gives you these Newman-Penrose scalars in the QR literature. Then we get to 6 points. And that's not something that, you know, what are they for? It's not something people talk about. Why do we have 6-point amplitudes? Of course, I mean, if you take the point that the amplitudes are the defining thing, 6-point amplitude is there. It's important, right? So what is it? And the point here is that if you're defining gravity through the scattering amplitudes, you're putting the quantum physics first. You're baking quantum physics in. Amplitudes are quantum mechanical. That means that you're baking uncertainty into the physics. The uncertainty principle is certainly there. The uncertainty principle means that the expectation value of products of operators are not equal to products of expectation values of operators. There's variance. That's what the uncertainty principle is all about. So here I'm looking at, you know, an expectation value of 2 Riemann tensors in the far future. That's what the S's are here. The S's are time translation operators. So these are Riemann tensors in the future. That's not going to factor into the expectation value of 2 Riemann tensors. Now, this is a 6-point amplitude. And one way to see that is to replace, you know, the Riemann tensor is basically just a package for an A plus A dagger, some spinor stuff, some Fourier transform stuff, but it's just got some creation and annihilation operators. So if I want to expand this thing out, say at some low order, I can forget the S dagger, just keep the S lowest order, some T transition matrix. So I get a transition between 2 particles here, and if I take these 2 A's and let them act on the P1 and P2 prime, I'll get a 4-point, 4 particles in the bra, 2 particles in the ket, so it's a 2 to 4, 6-point amplitude. So this thing here on the left is a 6-point amplitude plus other stuff. These things on the right, by the same logic, are 5-point amplitudes. So this would be a product of 2 kinds of 5-point amplitudes. Clearly, they're not equal. Now, on the other hand, in the classical, you know, if your state, I mean, we put in initial conditions in our state. So if you arrange the initial conditions so that the process, the dynamics, is a classical, it's in the domain of validity of the classical approximation, then this factorization should occur. So there must be some way in which this object on the left-hand side, an expectation value of 2 Riemann tensors on a classical state, factors into the expectation value of 2 separate Riemann tensors. So this becomes, you know, if you look into this, it's interesting. It becomes a constraint on the classical expansion of scattering amplitudes. It was a topic of Ricardo Gonzo's talk a few days ago. Now, it's useful in this context to expand the amplitude. I just want to talk a little bit about what the structure is like and speculate about it. It's useful to expand the amplitude in this sort of H-bar expansion. So there's some dominant power of H-bar downstairs, and then this is a wrong expansion, right? So there's some series here. So the N and L here, by the way, that's N points, L loops. Now, it's useful to have a name for these things, you know. I mean, you know, it's the super classical bit and the classical bit and the quantum bits. I mean, you know, this gets more and more complicated. The more points and, you know, you start talking about, there are many, many kinds of super classical. It's a bit silly. So it's useful to have a name for them. I don't know what's a good name. One suggestion is fragments. You see, the things, you call them parts of amplitudes. Well, partial amplitudes is just a different thing, right? partial amplitudes, pillar ordered amplitudes. Anyway, so there are these bits, fragments. Let's call them fragments for now. So we can explode the amplitude up into these different fragments. It's the same expansion as was in Ludwig's talk a few days ago. Well, so some comments about this. So there's different ways of thinking about the expansion. You could think about it as being, well, there's something disgusting about expanding in H-bar to begin with, right? I mean, nobody really wants to do this. In particular, H-bar is dimensionful, and expanding in a dimensionful thing is, maybe not a fantastic idea. So it's useful to know that this expansion is equivalent to an expansion in dimensionless quantities. The dimensionless quantities are momentum transfers, like Mandelstam to momentum transfers, over the center of mass energy. So Q squared over S. That's what this expansion is. It's also the same as an expansion in large masses, like an HQET or heavy particle effective fields. Now, of course, the HQET expansion is a dimensional expansion, NB, like the quark mass, B quark mass. My advisor at Caltech managed to make quite a good career out of that. That's a dimensional expansion, so maybe it's okay to expand it much more. You can think about it whatever way you want. These are all the same. Anyways, in terms of these, these fragments, so the fragments are going to be indexed by this upper number here from the lowest order in H-bar up. You can start generating a bunch of relations by looking at these requirements of zero variance. So here's one example. There's an infinite number. Here's an easy example. So if I take the Riemann tensor and a momentum, and I measure its expectation of these things in the future, well, classically, that better factorize into an expectation value of the Riemann tensor in the future and an expectation value of the momentum in the future. So this thing here is a 5-point amplitude. There's an A and an A dagger in that Riemann. There isn't in the P. Or else you could say it's A dagger A in the P if you want to do. That's the way to think about it. So this thing will come out to be a 5-point. Again, this Riemann just expectation value 1 Riemann. That's a waveform type thing. It's 5 points. And this thing here, which is a measure of momentum, is a 4-point amplitude. There must be some relation between 5-point amplitudes and products of 5-point amplitudes and 4-point amplitudes. Now, if you look at this and restore the H-bars, you find that it becomes this particular kind of relation on these fragments. So this leading one here, you might call that the super classical part. Here you see it's not super classical, it's actually classical. It computes the actual classical expectation value. But this one here, this leading fragment, must be related to this leading one loop fragment, must be the leading tree one and the leading 4-point. So diagrammatically, there's a relation like this. So the dominant in H-bar part of the one loop 5-point has to be the tree 5-point and the tree 4-point. It's a pretty similar, familiar story from the 4-points. Continues, we can just throw down as many of these relationships as you want. I can put 2 momenta here in addition to a Riemann tensor. That will again be a 5-point object. And then classically, that must factorize into this product of 3 things. And 5-point amplitudes times 2 4-point amplitudes now. So when we look in the details, you'll find that the relationship is a relationship on 5.2 loop amplitudes, factoring into 5-point trees and 2 4-point trees. So something in sort of like this. And of course, you can keep going. Right? There's also subdominant relations in here. So there's really quite a lot of information. So this leads to, well, just some comments on the structure of these amplitudes. So I'm thinking about 2 massive particles going to 2 massive particles plus n gravitons. These amplitudes here. So at loop order, there's a bunch of terms which are iteration terms. And this is 4 points, very familiar. Right? So these are just all the iterations of lower things. There's one term that has the classical information, and then there's an infinite number of terms that contain quantum information. So this thing here is the bit that you want for the classical physics. You want the quantum physics, well, you have to do all this other. Now, it's exactly the same structure at 5 points. So the same sort of iteration structure. There's one bit of classical information, and then loads of bits of quantum information. But after 5 points, it changes. The situation changes a bit. So to illustrate that, I made this table here. So this is how I think it works. So these are on the table, I'm looking at 3, 1, 2 higher loops and various points, 4, 5, etc., 6, 7 points. And what I've written in the table here is the part of the amplitude in this fragment. The leading part with classical scaling, so the classical bit. So, we know what to do at 4 points. It's easy, right? It's just the leading part of the 4-point tree. At one loop, you have to dig one order down, right? There's the super classical and then there's the classical bit. At 2 loops, you have to go 2 orders down to get the classical bit, and it's something you have to compute. It's the same for 5 points. So there's a 5-point tree that has classical information, a 5-point loop has classical information, etc. But at 6 points, it's different. Now, the way it becomes different is that the thing that has classical scaling is already an iteration term. So the classical scaling part of 6 points, it's at 1 loop. There's nothing at 3. At 1 loop is a product of 2 5-points. And thereafter, you just dress it with more and more 4 points. That's how you build up all of these 6-point algebra. 7 points, the leading thing is a cube of a 5-point tree. At least these are what we're getting from these zero-variance relations. And it's going backwards, not forwards. So now I think these kind of relations are a little bit interesting. So as I said, I'm trying to think about getting gravity without having any Lagrange, any path integral. So as far as I can tell, if you want to see, say somebody hands you a bunch of amplitudes and asks you, are these amplitudes coming from a theory with a path integral? The question you should ask yourself is this: do they satisfy these zero-variance relationships? If they do, then I think there's a path integral. If they don't think so. It's something else. But maybe, this is very speculative. Maybe this is the structure in the scattering amplitudes that's the path integral. The realization, that what's left from the path integral when you just have the amplitude. Now, it'd be very nice to prove these relations. I mean, we're cooking them up just by requiring zero variance, so requiring that the uncertainty goes away when you do a classical measurement. So it'd be very reassuring to show that they are true. It would be even better to show that they aren't true, right? Because if they don't hold, that would be telling you that there's some situation where the variance in some measurement is larger than you think. The uncertainty is bigger than you would have thought. I don't know, maybe that happens. I mean, we're trying to think about gravity. We're trying to think about gravity from a point of view of amplitudes. You're putting in the quantum physics. Maybe sometimes the variance is bigger than you thought. And then sort of more technical comment. So thinking along these lines leads to an iconal type formula for what all of these amplitudes would look like. So this is the classical parts of all of the amplitudes, loops and legs, any number of loops and legs. So it's basically a generalized iconal. There's the 4-point bit, just the usual thing. That's the Fourier transform of the 4-point amplitude. But there's also a 5-point bit, which gets exponentiated, and it's multiplied by a creation operator. So if you expand this twice, you'll get 2 creation operators, for example. That will give you a 6. Well, that's so this is a formula for 2 going to 2 incoming particles going to the future. So if we get 2 creation operators acting here, it's 2 photons and 2 gravitons in the final stage. So it's 2 to 4, 6 points, and it's given by the square root of 5 points. That's sort of, this is a formula that encapsulates these ideas. I'm a little bit vague on what these integrals are. We put down a more detailed proposal. What's a proposal? It's not proven. Indeed, I imagine there's more complicated versions possible, but I wrote about it in this recent paper that Ricardo spoke about. And I know that our friends Paolo, Carlo, Rodolfo, and Gabriele have been thinking about some similar ideas. Some work that will appear soon in the new year. Okay, well, that's all I wanted to say. I think amplitudes certainly proven useful in gravity. I think we've learned a lot I think that speaking as languages person, have learned a lot from gravity in recent years. And I think we're just scratching the surface. I think there's much further to push this. So, well, all that remains for me to do is to ask everybody to join me in thanking the organizers for going to the effort of bringing us all together. So thanks, Vi, Enrico, Julio, Mikhail, and Sasha. I will clap, presumably, for everybody else. Good, thanks to you. And I look forward to the next QCD Meets Gravity.
Well, thank you. And thanks for all the great talks that people gave. It was really wonderful. So I guess we're done.
That's it.
Well, can we see if there are any questions for Donal after this provocative talk?
I have one.
Yeah, please, of course.
Yeah, may I?
Please do so. Yeah.
Well, first of all, I sympathize very much with the, getting everything from on-shell amplitudes. Being a string theorist,
Oh, that's right.
I mean, you just have an S matrix, and by the way, it is well defined in Minkowski spacetime. Now, I have just one question about recovering classical physics, which is the singularities of, of classical general relativity. So it seems to me that the amplitude approach does even better in the sense that I don't see, for instance, in your 3-point function or 4-point function, any evidence for a singularity like you have in Schwarzschild. Does it mean that somehow the quantum mechanical problem is better defined than the classical one? After all, we know that, for instance, also in electrodynamics, the charge of the electron gets an infinite self-energy. In the quantum theory, you only get a logarithmic divergence. Maybe in string theory, you don't get a divergence at all. So I wonder whether you recover the good side of GR, but not the bad features by playing the amplitude game. The other question, on the other hand, is how do you cope with cosmology, for instance?
Yeah. Well, that's right. Well, cosmology is what I completely punted on.
Coin. For the rest is.
Cosmology, of course, is a really exciting and challenging topic. I mean, we heard a little earlier in the meeting from Gui, that perhaps these cosmological correlators, are a place to start. But obviously, it's very early days, I think, and that's that topic. And absolutely, I actually had cosmology in my list of exciting things about general relativity in an earlier draft of this talk, and I removed it. I thought that was probably too risky. But it's an interesting question you ask about the singularity at the origin in Schwarzschild. So in our amplitudes, in the 3-point amplitude, we're putting in, I guess what you should do is put in an initial state, for that massive particle, which localizes it somehow, so some classical localization. And now when I've done the integrals, for simplicity, I've taken that localization. I've ignored the effects of that localization. So we just put in the 3-point amplitude, and we didn't really put in a wave function. We said the wave function doesn't make a big difference. But if you were to keep that wave function in, you would blur out any singularity. So there wouldn't be any singularity. But in doing the integrals as we've done them, you would recover the singularity at the origin, essentially because it's an interchange of limits problem. You shouldn't go to x = 0 and trust our integrals. That's where the singularities emerge from.
Mm-hmm. But do you see it in a scattering?
Well, you wouldn't, I don't think you would really, because I mean, when you scatter the particles, if they start to get close together, genuinely close, so that you start to, want to bash into that singularity, that's where, the approximations go out the window and you'll have the fully quantum scattering. It won't be classical. So yeah, it'll turn out different. Yeah, I know. I think you're, I think fundamentally, the scalar particle is a quantum of a scalar field. So it isn't, there isn't a singularity that you get in the classical theory. I mean, there's just some scalar field stuff. So yeah, I mean, I don't really think those singularities should be so scary.
Yeah, so I mean, it's not clear to me that it makes sense to test the distances at which the classical singularity occurs.
Yeah, I think if you try to do that, you'll reveal more quantum structure, and the calculation will be different. The quantum calculation. Yeah.
Just one point of credit. I mean, this last formula you wrote, it's already in some older papers by Ciafaloni, Golferai, and myself.
Oh, okay.
With the with the exponentiation of the 5-point function.
Maybe we should email me about that. Okay, thanks for that.
Do we have a final question, I believe, from Yilber?
Oh, yes. Hi, Donal. Thank you for the very nice talk. So if you go back to your table, like you were doing this counting for 2 massive lines and then the remaining to be massless. But
sorry. I tried to go back. Oh, I see. I somehow managed to, sorry, let me share my screen again. I think that happened.
Yeah, I was asking that in your table, how does your table change if you now consider 1 massive line and then the remaining ones to be massless?
I see. You want me to do scatter radiation off rather than 2 particles? Yeah, it's a good question. I don't really know. I mean, I guess to make sense of the question, I would probably need to put in a coherent state. So I'd have a massive particle scattering with a coherent state. So I'm still doing classical physics, right? Yeah, it would change a lot. But I don't know the answer. I'm not sure. Yeah. I think that's an interesting question, but I don't know the answer. For another paper.
Okay, let's thank Donal again.
Thanks.
And all the speakers and all the spectacular participants and all the